Hello, today we are doing some hard physics, some real optics, so let's get right into it. We are looking at the diffraction of light in the double slit experiment, and we're going to look at it qualitatively and quantitatively. So let's start qualitative. What is diffraction? It's when a wave hits a barrier or an opening and it spreads out from that barrier. So this is what lets your mum shout at you from the kitchen, that shout to go through your bedroom door and allow you to hear that it's time for dinner. Okay, so this is your mum and she shouts, and when she shouts, sound waves ripple out from around her head. They hit this doorway, and from this point, they spread out. So from this point, they re-spread out so that you can hear them, even though you're not in direct line of sight. Sound doesn't just travel straight through that door and miss everything that's, you know, some people might think it travels straight through the door and it'll miss you, but no, when it hits the door, it spreads out. That's what diffraction is. This can happen for any type of wave. So we're looking at light waves. And so the classic experiment is the double slit, or as if there were two doors to your bedroom. What we think about is we have red laser light shining towards these two slits in a piece of card or something. These two slits are usually incredibly close together so that a single beam of laser hits both of them at once. And this laser beam comes in, all the wavelengths are parallel to each other, but once they hit this spot, they then spread out, just like the shout spread it out from the doorway. Now we're using a red laser here, however I'm going to use blue for this second slit here so you can see more easily the interaction between one wave and the other, because they are going to interact. All right, now right in the middle here at this spot here, we have the light from one slit overlapping with light from the other slit. The lines themselves on the line is the crest of the wave, and so this is where red crest is meeting up with blue crest. Well, really, they're both red, but red crest with red crest, when you have a crest on top of a crest, they add together, you get constructive interference, really bright light. Right next to them though, right here, you have the red crest, but it's right in between two blue crests. That's a spot where it's a trough. So when you have a crest with a trough, they cancel each other out and you get no light or very dim light. And then after that, we have crest meeting with crest. Then we have crest meeting with trough again, etc., etc. If these lights were allowed to continue forward and they'd hit a screen, a wall or something, you would see where this spot is coming, that would make a very bright spot on the wall, bright red light. But then next to it, this dark spot is going to make a spot where there's nothing. Okay, and then this constructive spot, you'd get again a spot with a lot of light, then nothing, then a lot of light, then nothing, then light, then nothing, then light. And the same would happen on this side, and they get dimmer as they go down. Okay, so what's causing this? Why at this spot here do we have destructive and this spot we have constructive? It's to do with the wavelength itself. At this middle spot here, because the distance from the slit to that spot is the same no matter which slit it comes from, that means the waves are in line with each other. They're going to constructively interfere. However, in this dark spot here, right, this bottom one traveled a shorter distance to get there. Let me get there. So for this spot here, this bottom slit, the light travels a shorter distance to get there than this top one. Okay, how much shorter? Exactly half a wavelength shorter. So that the bottom light came in like this, but the top light, because it has to travel half a wavelength longer, it started up here and now it's out of phase by half a wavelength. So but by the time it arrives there, you've got a crest and trough cancelling each other out, and the overall effect is no light, no intensity at that spot. At the next spot down, how much different is the path of the wavelength? It is different by a whole wavelength. So now one of them traveled like this and one of them started off one whole wavelength ahead, making them crest with crest again, nice and in phase. So if you wanted to know where you get bright spots along where you get bright spots along here, you would need to know what the wavelength is, right? And you need to know, and you would get bright spots every time you have a whole number of wavelengths. So in this middle spot here, when that path difference between the top slit and the bottom slit, these lengths here, when these lengths are exactly the same, that would be 0 times the wavelength of difference between them, right? They're exactly the same. For this next one down here, you would have 1 wavelength difference between the top path and the bottom path, right? Exactly 1. For this spot here, it would have to be 2 wavelengths difference in the distance that the light's traveling. Okay, if you want to get the spots in between, it'd be half wavelength. So it'd be half, 1.5, 2.5 to get these middle in between spots. Okay, that's exactly what this part of the equation up here is describing. M times wavelength. M is an integer number like 0, 1, 2, 3. These are all the different bright spots you get along your screen. Okay, and the bright spot is going to be equal to the distance between the two slits times sine theta. And sine theta is going to be an angle between the bright spot you're looking at and the center of the two slits. Let's look at that in a bit more detail now. So if I delete all of this. So we have our two slits here, and I'm going to make them nice and obvious. Although in reality, you've got to remember they are much closer together than I can draw here reasonably. And on this end, we have our screen. Now we're trying to look at our bright spot. So we've got bright spot number 0 in the middle, but let's look at bright spot number 1 here. This is 1 full wavelength of path difference between two spots. Okay, that means that this distance and this distance are different by exactly 1 wavelength. In fact, if I drew a line across here, making this a right angle here, this length down here, which I should have done a different color, this length in green here is the difference in path length, is one full wavelength, because that's what's been added on in order to create constructive interference. There needed to be 1 extra wavelength in this bottom one compared to this top one here. Okay, so this equation should start to make a lot of sense, right? Because we're saying that 1 wavelength, that's this length here, is going to be equal to d sine theta. And what's d sine theta? Well, d is the distance between these two slits, and theta is, let's do it in blue, theta is this angle right here, okay? It's just simple trigonometry, right? Sine opposite over hypotenuse, nice and easy. However, this angle here is so tiny and this distance here is so tiny that we can't really measure them in real life, so it's not very useful. We can make some assumptions that allow us to work out this angle pretty accurately. What that assumption is that the length between the slits and the screen is much longer than this distance here. What that does is it makes these two blue lines pretty much parallel to each other. Once we make that assumption, we can actually say that theta is about the same angle as the angle between the middle of the screen and this first point, right? From the slits to the middle of your screen, the 0 spot, the angle between that line and the line from the middle of your diffraction grating to your first bright spot. That angle is about the same. There's a lot of parallel line maths that you can do to work out that this angle is the same as that angle there. Suffice to say for this course that they are the same and that this one is much easier to measure. So all you need to do, well, let's see if we've got enough things that are easier to measure. easy to measure. Your angle, yes, these I'm expecting to be millimeters apart or centimeters apart, not micrometers apart. So we can measure this. This distance here, I'm expecting to be in centimeters or meters. Easy to measure. M, you just need to count from the middle how many there are. M, M of 0, M of 1, etc. Wavelength, no, you cannot measure the wavelength with your own eyes. However, I'm assuming here that we're using a normal red laser, which has a wavelength of about 650 nanometers, or in SI units, 650 times 10 to the minus 9 meters. So if we can get everything, but the distance still remains hard to measure. However, if we have everything else, we can actually calculate the distance between spots on your diffraction grating. And once you've done that, if you put in a new wavelength of light through your diffraction grating that you don't know the wavelength for, because you've calculated D, you can then go backwards and calculate wavelength for the unknown light.